All right, everyone, welcome back to Calculus 2. So last time we were exploring the concept of series, which remember, it's the sum of all the numbers in a sequence, aka an infinitely long list of numbers. Now, last time we were able to find out what some series summed up to. And those two types of series we were able to do that with were geometric series and telescoping series. So geometric series where we had a fixed number to the n, we added up all of its powers, and we have a special formula for doing that. And then we had telescoping series, which had a function and then a very similar function being subtracted from it. And we were able to kind of cancel all of those out and see what would happen with those. But unfortunately, those two types of series are really the exception. We were able to figure out what those added up to, but in general, we'll only really be able to know whether a series converges or diverges, not what it sums up to specifically. And we had a really good question last time about that. It might have been after class or maybe at the end of class. Why would we care about a series if we couldn't even find what it was going to sum up to? It's because when we get to our next part of the class with these polynomials are only going to work where their series converges. So we want to make sure we know how to figure out when a series converges or not, or to use those polynomials I've been hyping up the whole time. Anyways, let's go ahead and get started here with our first series test. Now, for the next few classes, we're going to be learning some ways of determining whether or not a series converges. And we're going to be doing them in increasing order of importance, which means that today's test is probably the least important of all of them. It's still important enough for us to teach it to you, but it's probably the one you'll end up using the least once we get going here. Does someone have a question? No one have a question? Okay. All right, let's go ahead and get started. So what is the integral test? It probably has something to do with integrals. Well, let's say we have, let's write out what the integral test is. Suppose we have a series, S is the sum from n equals 1 to infinity of a sub n, where the sequence has the formula an is f of n. So this is our formula for our sequence here. If a sub n satisfies the following three conditions, let's see, so what are these conditions here? F of n is continuous. So we need this to be continuous so we can integrate whatever it is. We need an to be decreasing, and we need an to be positive. So we need the sequence to satisfy these three conditions before we even begin using the test. So this is kind of like step 0 of doing the test, is we need to make sure that whatever sequence we're adding up in our series satisfies these conditions. Because if it doesn't, we can't use the integral test at all. All right, now let's say it does satisfy all of these. Then the series S converges if the integral I from 1 to infinity of f of x dx converges, and S diverges if I diverges. So pretty much what this is saying is that we take whatever formula we have that we're adding up for our series, and we throw it into an integral instead. And what's going to happen is when we do that integral and we get a result, if that result is diverges, then the series that we originally had will diverge too. And if it converges, then the series will converge as well. So the integral and the series will end up doing the same thing. provided we have these three conditions working for us before we attempt this. All right. Now, why does this work? Let me kind of draw a kind of a brief picture and give a little explanation as to why this works. Not be a rigorous proof or anything, but it's at least going to kind of show us what's going to happen. So let's take a look at the integral. This is what the integral represents, right? So let's say we start at 1, and let's say our f of n looks like this. Then what we're doing is we're finding the area under the curve starting at 1 and then going out to infinity. So this was our integral from 1 to infinity, f of x dx. So that has a certain area. And kind of surprisingly, back in the integral chapter, we found out that sometimes this integral can give us an infinite amount of area, but then sometimes it can go to 0 fast enough to give us something finite, even though it kind of stretches out forever. So it's kind of a little bit strange, but we can get finite values from this or infinite values. It really just depends on what our function is. That's the integral. Now let's take a look at our series. So what we're going to do with our series is we're going to imagine it as a bad Riemann sum. You guys remember what Riemann sums were? Riemann sums were kind of like the precursor to integrals, right? A Riemann sum is where we added up all of those really thin rectangles together, and that gave us something that was really close to the area under the curve. Now, what do I mean by a bad Riemann sum? Why is it bad? Well, it's bad because this is going to be the height of all of our boxes, and then we're going to stick a times 1 in here, and this is going to be the width of all our boxes. So Riemann sums are nice because eventually their width goes to 0, right? And we have a bunch of them. But this is going to be a bad Riemann sum because its width is going to remain at 1. So what is this going to look like? We have the same function right here. Remember, this is also f of x. Then what we're going to do is we're going to have these rectangles. So we have these rectangles, and we're finding the area of these. So we go from 2 to 3. Then we have the one going from 3 to 4. And then we have the one there going from 4 to 5, and so on. So we have these kind of rectangles instead of the actual area. Now, the reason why the integral test works is because these are about the same size as one another. You might be like, oh, well, this one could be bigger right here. Well, it turns out that these aren't going to be that much bigger compared to the rest of the area right here. And the details of that are in the proof, like how much bigger this will be, or maybe smaller if we decided to use right-hand endpoints for this, because we could have draw the rectangles like this as well instead. But what they're saying is that the integral and this kind of bad Riemann sum are about the same size. So if this converges, then so will this. If this diverges, then so will this. And I like to think of it as the series and the integral sort of share the same fate. So if you want to know what happens to your series, then you see what happens to the matching integral instead. So that's going to be the big idea behind this integral test here. All right, so let's actually but before I start the example, I want to give a bit of a warning here. Watch out for this. The value of the integral might not be the sum of the series. All right, so then let's say, for example, this integral right here, the area under this curve was like 2 or something like that. That does not mean that if we add up the matching series, we're going to automatically get 2. That's kind of a common misconception. It's just that since this went to 2, this integral converges, so we know the series is going to converge. But we don't know it's going to add up to 2. And in fact, most of the time, it's not going to add up to what we get for the integral at all. So that's kind of a warning here. So the value of what we get from this integral may not necessarily be what our series is going to add. All right, now let's look at an example. Okay, use the integral test on the series n equals 1 to infinity of arctan of n over n squared plus 1. All right. Now, if we look at this, we know about two series already. We know about geometric series and we know about telescoping series. But because of this arctangent, this doesn't look like either one of those. So we can't use anything that we've learned last class. And if we try the test for divergence, which we learned 2 classes ago, this will give us 0. And remember, we can't include anything from the TFD if we get 0. So we have to use our new integral test here. Now, remember, we need to check the 3 conditions first before we use our integral test. David, do you have a question? Okay. All right, so let's go ahead and check the conditions here. So the 3 conditions were continuous. Is this a continuous function? Well, arctan is always continuous. It kind of just looks like this, so that's fine. And the bottom, well, it may cause us problems if the bottom's 0, but n squared plus 1 is never going to be 0. So yes, this is going to be continuous. We can check that out. Okay, is an positive? Well, let's see here. If I plug in a positive number in for arctan, I'm going to get a positive number out. Because let me remind you guys what arctan's graph looks like. It looks like this. So if I plug in something on the positive end over here, I'm going to be above the x-axis. And then this is always positive. So I have a positive over a positive. So that's going to be positive as well. And then finally is an decreasing. And by the way, when I say decreasing, it doesn't need to be decreasing for every single step. It just needs to eventually be at a point where it's decreasing. So it can kind of have its like, wild youth or something where it bumps up or down for a little bit, and then it eventually kind of settles down and just kind of tapers off after a while. So as long as it eventually decreases, that's really what counts. So arctan, well, that is getting bigger up here. It's limited to being pi over 2, right? So this is kind of capped off by pi over 2, but then the bottom here can get big without n. So this is getting really, really, really huge. So something that's close to pi over 2 over something getting bigger, that number is definitely going to be decreasing and it's going to be going to 0. All right. Can we take the first derivative to find if it's increasing or decreasing? Yeah, that's a very good point, Sam. So if you're unsure as to whether your function is increasing or decreasing, you can do the first derivative of it. Because remember, the derivative of the function tells you if it's going up or down. If your derivative is positive, it's increasing. And if your derivative is negative, it's going to be decreasing. So yeah, if you want to definitively prove for sure that this is decreasing, you could look at the first derivative. But if you're confident, if you kind of look at this and you're like, yeah, I'm pretty sure this is decreasing, then you can kind of just go with that. All right, so we've satisfied all the conditions. So now what that means is we're going to look at an integral instead of a series. I'm going to do the integral from 1 to infinity of arctan of x over x squared plus 1. So I'm going to do this integral right here, and the result of this integral, whether it converges or diverges, will be the same as for my series. All right, well, these are always improper integrals, so I'm going to replace them with a limit. And then we'll just focus on the integral part. All right, so let's kind of scrape the rust off of our skills here. How would we do this integral? Does anyone see how we would do this one right here? Right, yeah, I see some u subs. That's absolutely right. So I'm going to do u is arctan of x. And reason being is that the derivative of arctan is 1 over 1 plus x squared. And that's really convenient because we have exactly that in our integral here. All right, so that means that we're doing the limit as r goes to infinity of the integral from x equals 1 to x is r of just u du. Because the u is the arctan and then the du was the rest of the stuff. All right, now this is a pretty easy integral to do. It's just going to be u squared over 2 from x is 1 to x is r. And then we could plug back in our original u. So we have arctan of x squared over 2 from 1 to r. All right, now let's plug in our 1 and our r, and then we'll focus on doing the limit part. So if I plug that in, I have the limit as r goes to infinity of arctan of r squared over 2 minus arctan of 1 squared over 2. All right, now let's see here. This is just going to be some number. This is going to be pi over 4 squared divided by 2. Now, what is this going to be? Well, let me ask you this. What happens to arctangent as its input goes to infinity? If we look at our little graph up here, what is arctan heading to as its inside gets really large? That's right. It's going to level off at pi over 2. So this is just a fancy way of saying pi over 2 squared over 2. And then arctangent of 1, what makes tangent be 1? It's pi over 4. Okay. Now we could simplify this and combine fractions and get specifically what this is. But remember, it doesn't matter specifically what number this is. All we really care about is that the integral converges. So since the integral I converges, then the original series, n equals 1 to infinity, of arctan of n over n squared plus 1 converges by the integral test. And you guys dodged a bullet this semester. So if you were doing this, like taking a paper exam, we would have you write out a little sentence like this. We always want to state which tests we use and why it's giving us the result that it is here. But you guys just have to pick stuff on multiple choice. So you won't need to type anything like that or anything. But you should know what converge is. Why is it pi over 2? Because as the input of tangent gets really close to pi over 2, like here's the graph of tangent of x. As we get really close to pi over 2, tangent goes off to infinity. So arctan flipped things around. So now the inside's going to infinity, and then the output is going to go for pi over 2. Can I explain why I used r? It's just a different variable other than x. So it's an improper integral. So we needed to have something going to infinity. And r is usually what I use for that. All right. So let's go ahead and have you guys try this. So, oh, is this not working very well? Can you guys hear me? Is it okay?
No, it works fine. Just sometimes, you the audio kind of fades away, but it comes back.
Oh my God. Yeah, I'm sorry. My computer's not working at all today. It's something with my microphone on my headphones. Yeah, sorry about that. Anyways, so let's see. We use the integral test to determine if the sum from 1 to infinity of n e to the negative n squared converges or diverges. All right, why don't you guys take a few minutes and take a try at this. Can we assume it passes all 3 conditions? You should check to make sure it does. Make sure it's continuous, positive, and decreasing. Negative n squared. Usually if I write a coefficient, it'll be in front of the variable. Does it converge? We'll see. He has another minute or so. All right, so we got diverges as well. Diverge. It seems like diverge. No, we don't have a good consensus on this one. This will be interesting. Your brain's on Monday mode. All right, let's take a look at this. Let's settle this. So, first of all, before we do anything, we need to know if this satisfies the conditions for the integral test. Okay, so let's look at n over e to the n squared. All right, well, let's see here. Is this going to be continuous? Well, let's see. N is continuous and e to the n squared is continuous since it's an exponential function. So yeah, there's going to be no problems in that. And e to the n squared is never equal to 0 either. Is it decreasing? Well, let's see. So this is where the hierarchy of functions comes in. So n does go to infinity, and so does e to the n squared. But remember, exponential functions go to infinity more quickly than this does. So since this is getting much, much larger faster than this is, that means our fraction's getting smaller. So it is going to be decreasing. And is it going to be positive? Well, this is always positive as long as we put positive n in there, which we are. And this is positive no matter what. So, yep, it satisfies all three of them. All right, so let's go ahead and do the integral here. So our integral is from 1 to infinity, x e to the negative x squared dx. All right, so as always, this is going to be an improper integral, so I'm going to replace my upper bound with an r. That's the improper part. And then now I need to do the integral. And the way I'm going to do this integral is I'm going to do u is negative x, or I'm just going to do positive x. So du will be 2x dx, and then we have du over 2 is x dx. That's exactly what we're going to have in our problem here. All right, so we have the limit as r goes to infinity from x equals 1 to x equals r. And then we have du over 2, so 1/2 du, and then e to the negative u. Now, you could have also done this with u as negative x squared. That would have worked fine as well. So don't be alarmed if I didn't use negative x squared. All right, so now I'm going to integrate this, meaning I simply just divide by a negative. So the limit as r goes to infinity of negative 1/2 e to the negative u from x is 1 to r. All right, and then I plug everything back in. So I have negative 1/2 e to the negative x squared plus 1/2. Well, whoops. Yeah, no, that's right. And then I do it from 1 to r. So I have this e to the negative r squared plus 1/2 e. All right, because I just plugged 1 in there. Oh, no, sorry, e to the negative 1. Whoops. There we go. All right, now let's take a look here. So as r goes to infinity, we have e to the negative infinity, right? So what happens to your exponential function as the input goes to infinity? So e to the negative infinity. It's going to go to 0. That's right. Yeah, because it's technically 1 over e to the x as x goes to infinity. We're going to have the whole thing going to 0. So this is just a big old 0 right here. And then we have 1/2 e to the negative 1, or 1 over 2 times e. So we get 1 over 2 times e right here. And then what does that mean? Does that mean our series sums to 1 over 2e? It doesn't mean that, but it does mean that our series is going to converge. So the series from 1 to infinity, n e to the negative n squared, converges by the integral test. All right. There we go. So we know this converges. Now we don't know it converges to a particular number. Like we don't know it converges to 1 over 2e. We have no idea what this specifically adds to, but it will converge to something. All right, I wanted to use this on another function here, or sorry, another series. I want to take a look at this series. Let's say we have the sum from n equals 1 to infinity of 1 over n. Very simple looking series here, but it's not geometric, it's not telescoping, and this goes to 0, so we can't use test for divergence. So the only thing we have to analyze this again will be the integral test. So let's check the conditions. Yeah, let's check the conditions here. So is it continuous? Well, 1 over n is continuous except when n is 0, but n is not going to be 0, so that's okay. Is it positive? Well, yeah, if we put positive numbers into there, it's going to be positive. And is it decreasing? I think this one's the most obvious decreasing yet, because as our n gets larger, 1 over n is going to get smaller. So it satisfies all the criterion, so let's go ahead and do the integral. Okay. I'm just going to be a little bit lazy on this one. Normally, I would have to write this as the limit as r goes to infinity of 1 to r. Actually, I'm going to do that anyways. I'll set a good example. We should do that. Okay, so we have our limit here. Can we not just tell it converges to 0? Surprisingly, this series is not going to converge at all. And here's why. You may be thinking of the sequence. So as a sequence, without adding it up, 1 over n will converge to 0. But as a series where we're adding up all of these reciprocals, who knows what might happen? Although I just spoiled it. It's going to diverge. So why is this going to diverge? What's going to happen? So this is going to turn into natural log of absolute value of x from 1 to r. All right, so then this will be the limit as r goes to infinity of ln of r minus ln of 1. All right, now ln of 1 is 0, so we can just get rid of that. And then what happens to this limit? Well, Justin has the right answer here. The limit goes to infinity because as the inside of natural log goes to infinity, the overall output goes to infinity as well. So we end up with positive infinity, meaning the integral diverges. And remember, whatever the integral does, the series will do as well. So we know that the sum from 1 to infinity of 1 over n diverges by the integral test. And this is kind of surprising, right? Because these numbers, if we look at what this is 1 plus a half plus a third plus a fourth plus a fifth plus a sixth. It seems like these guys are getting smaller and smaller, and they are. I mean, that list of numbers will go to 0. But the thing is if we add them up, it kind of builds over time. So for example, in order to get higher than 2, I guess we would need to add up these 4 right here. And then in order to get higher than 3, we would need to add up at least past 1/10 and so on. But whatever boundary you set, it's eventually going to pass it if you add up enough of these terms. That's what the integral test is going to do here. You ever have to specify if a sum diverges to negative or positive infinity? No, it's just diverging or converging here. So the difference between sequences and series is the series adds all the values, and the sequence is concerned with what will happen when the value of n goes to infinity. Yeah, that's absolutely right. So if we're looking at the limit of this as a sequence, this list of numbers is heading to 0. But then if we're adding them together, that's what the sigma means, then it's accumulating over time. And even though they're small numbers, they're accumulating fast enough to where this goes to infinity. Now, the thing is that this goes to infinity incredibly slowly. So I usually have this as a homework assignment, but I guess I can't do that with Chronos. If you want to have this sum exceed 100, and it will eventually because it's going to infinity, right? You need to add up 10 to the 43rd terms. So you're going to get to numbers like 1 over 10 to the 43rd before you're going to end up getting past 100. But you will get past 100, and you'll get past 1,000. And every number beyond that, but it'll take an exceedingly high number of terms. So this diverges, but it diverges very slowly. All right. Now, what we could do here is we can generalize this result and make a new type of test, because we see rational functions quite a bit, right? We see a polynomial over a polynomial pretty often. So we want to know what happens when we see those in a series. So what we're going to do is we're going to see what happens if I replace the power on the bottom with any power we want. So let's see here. So we have 1 over n to some power right here. This could be any number we want. Now, depending on what this power is, this series may converge. It definitely doesn't work for 1. It's going to diverge for 1. But what about other p-values here? Okay, so what we're going to do is we're going to split this into cases. We already dealt with p equals 1 up here. So what I'm going to do is I'm going to split it in half based on that. I'm going to do p greater than 1, and then I'm going to do p less than 1 afterwards. All right. So for all the conditions are going to be satisfied no matter which p-value we pick for the same reasons that it worked for this. So I'm not going to write those. I will write my improper integral now. So I'm going to do the improper integral if p is bigger than 1 here. I'm going to go from 1 to r, 1 over x raised to the p. All right, now technically, this is the integral x to the negative p, right? That's how the negative exponents work. So if we just use the power rule here, we can integrate this. So I'm going to add 1 to my power. So I'm going to have x to the negative p plus 1, and then I divide by the new power, which is also known as 1 minus p. All right, and then I'm going to go ahead and plug this stuff in. So I have r to the 1 minus p over 1 minus p minus 1 over 1 minus p. All right, now let's think about what this is doing. So we have a number that's getting really big, but then it's this 1 minus p power, right? So depending on what this power is, that could greatly change the outcome of what this limit's going to be. Well, let's see here. 1 minus p, that's actually going to end up being negative, because if I just add the p over, I get that p is greater than 1, which that's what we assumed in the beginning. So it turns out that 1 minus p is negative. So let me ask you this. If I have a really huge number and I raise it to a negative power, is it going to be really small or is it going to be really big? Something huge to a negative power. That's right. It's going to end up being really small because you're doing 1 over that huge number, and that's going to be tiny. So this limit's going to 0, and then we just get this number here, whatever number that is. Remember, the integral test, it doesn't matter what number it is, it just matters if you get a number or not. So this is going to converge. So it seems like for p greater than 1, this is going to converge as a series. So for example, 1 over n squared, that will converge as a series. 1 over n cubed, that will work. 1 over 1.0001, that'll work as well. We know it doesn't work for p equals 1. Why don't we try p less than 1? And this also includes negative numbers too. So maybe we have like p is -2, and then this will be n to the -2 on the bottom, so it'd be n squared on top. So that's just the same thing as saying n squared, for example. But it's any p-value less than 1. All right, so we do the same integral that we had before, only this time our power is going to be different. All right, so this is x to the -p. 1 to r. Can I repeat why the first fraction with r goes to 0? Yeah, because you have a mass, this 1 minus p is a negative number. This 1 minus p is a negative number, right? If you raise something huge to a negative power, that's going to head to 0. So that's why this limit went to 0 here. Why do we do x to the -p plus 1? Because we just did the power rule here. So I just added 1 to the power. All right. So now I'm going to do the same thing again. I'm going to get what looks like the same formula, and it kind of is, but p is different this time, remember. All right, so we plug in our 1 and our r just like before, but this time the limit will pan out a bit differently. Okay. So let's see here. Now let's see what happens with this. So we have -p plus 1, but I claim that, or this is the same thing as 1 minus p. And 1 minus p is actually going to be greater than 0. Because if we add the p over, just like we did before, we get that 1 is greater than p right here. So this is the same thing as saying this. So that means that this up here, this is a positive power. Now we're having something that's really big being raised to a positive power. That's going to go to infinity. Like, for example, something going to infinity and you square it, heck, it's going to go to infinity even faster than it was before. So this is going to go to positive infinity. And so that means that this is going to diverge. So if our p is less than 1, it's going to diverge. If our p is greater than 1, it'll converge. And if p equals 1, that's like really on the threshold. That's kind of like the boundary between converging or diverging. Then it's going to lean towards diverging. So we can summarize this in what's called the p-test. Okay, so for a series from n equals 1 to infinity, 1 over n to the p, the series converges if p is greater than 1, and the series diverges if p is less than or equal to 1. Why do I know for sure that 1 minus p is less than 0? Well, in this part of the problem, it was greater than 0 because 1 was greater than p. So in this part of the problem, it was 1 minus p is greater than 0. But the other part of the problem, we had that because 1 was less than p in that situation. Can you use the test for divergence for p if it's less than 1? Not if it's less than 1. If it's less than 0, then if it's a negative number, then you could, because then your thing would move up to the numerator. So if it's less than 0, we could have used the test for divergence instead. All right. So let's see here. So this is the p-test right here. This is called the p-test. It's very useful because it helps us deal with rational functions. Now, this is probably the most tempting thing to do, but let's say we were looking at this series, n equals 1 to infinity, 1 over n squared plus 1. For this one, we can't use the p-test because technically this isn't 1 over n to the p. This is 1 over n squared plus 1. So this isn't just 1 over something to a power. So we can't technically use the p-series here, even though it really feels like we should be able to do that, right? What do you guys think this series is going to do, if you had to guess? You think this series is going to converge, or do you think this series is going to diverge? Let's see, we see some converges. It looks like a lot of converges. Yeah, so it turns out this series is going to converge, and that's because it's going to act a whole lot like 1 over n squared. And if we looked at just 1 over n squared without that one, then we would see that the series converges by the p-test. Oh yeah, technically, yeah, you could use the integral test on this one and turn it into Arctan. So it's very, very observant, Christian. Yeah, that's right. So if we really wanted to do this, we could have done the integral test. But what we're going to learn next class is how we can generalize this p-test to when we have more terms than just one. But that'll be next time. For now, we're only kind of stuck with 1 over n to a power. All right. So I want to talk about one final thing before we get out of here. There's also something called the generalized p-test as well. All right, so generalized p-test. So what is that? Well, in this case, we're looking at a series sum from n equals 1 to infinity, 1 over n to the p, and then we have natural log of n raised to a power as well. Now this power may be different from this one right here. So maybe this one is 2, this one's -5, or something like that. So if we have this case where we also have log to a power as well, then we can still do the p-test, but it's going to be a little bit more complicated. So what's going to happen is the series will converge if p is greater than 1. So that's literally the same thing that we had last time. And notice that this doesn't say anything about q. So q could be like 100 billion or something. And if p is 2, then it's going to converge. But q could be negative 100 billion. And if p is 2, it's going to converge. So what this is doing trumps what this is doing here. And in the same way, the series diverges if p is less than 1. But notice that there's a little bit of a difference between this one and the previous p-test. This worked for less than or equal to 1. This only works for strictly less than. And again, this doesn't really care about what q is. So if p is like 1/2 and q is 100 million, then it's still going to diverge, even though that's a really high power right there. Okay, now what about p equals 1? If p equals 1 and q is greater than 1, we get a convergence. But if p equals 1 and q is less than or equal to 1, it's going to diverge. So the way I like to think of the generalized p-test, if we ever see these logs right here, is q is like a tiebreaker. So if p is definitively on the converge side, it's going to converge. If p is definitively on the diverge side, it's going to diverge. But if p is sitting right on the fence, like right at the power equals 1, then q will be the deciding factor there. So q would have to be greater than 1 for converging. But if they're all equal to 1, if all the powers are equal to 1, then it's just going to diverge. We apply the same principle to 1 over n to the p times q to the n. Well, in that case, q to the n is an exponential function. So in that case, that's going to dominate whatever's going on. Because remember, these are just logs. So if you put q to the n down there, whatever that is going to end up dominating the behavior. All right, so why don't we guys try this out? And then that's it for today. So why don't we take a look at the sum from n equals 2 to infinity of 1 over n ln of n cubed. Converge or diverge. And all we need to do is just use the generalized p-test that we just talked about up here. Yep, so we see some converge, and that's right, yeah, because so we have 1 over n, and it's just an n, so it's technically the first power. So in that case, we look at the p equals 1 here, and then we see that this 3 is bigger than 1, so we're going to end up with this converge. So that's how we use the generalized p-test with n to a power and then log of n to a power times that. Now, what we're going to do next time is we're going to learn how to deal with more general rational functions in a way that's similar to the p-test. It won't exactly be the p-test because we need to be exactly 1 over n to the p to do that, but it will be kind of similar. So that will be what's coming up next time. All right, so let me stop the recording.